Hello everyone, welcome back to my organic mechanism talk. As usual, I always remind you that arrow pushing is showing the movement of electrons in the reaction. Today we will talk about reactions about esters. We'll talk about how to make the ester. We'll also talk about the reactions of esters. So first, the most common way to make ester is acid catalyzed esterification. So that means you will use the reactant. One is carboxylic acid and the other one is alcohol. And then the acid need to be a catalyst. And then product is ester and the water is the byproduct. And the arrow pushing mechanism will be the first step is the protonation of the carboxylic acid. And the lone pair on this oxygen will attack this proton and then to make this protonated carboxylic acid. And then this carbon here will be more electrophilic. And the alcohol here, in this example, is ethanol. And lone pair on the oxygen will attack this carbon and then break this pi bond. So make this intermediate. You can see this oxygen is positively charged. And then the proton on this oxygen will transfer to the adjacent hydroxyl group. So this lone pair on the oxygen will attack this proton. This is called a proton transfer. And then the intermediate will have a good leaving group, water here. And so next step will be the lone pair on this oxygen, push back, form a double bond again, and kick off this water as leaving group. So that is the intermediate formed. And now we need to depronate another proton here on this oxygen, and we need just the base. Water can be the weak base here, and the oxygen of the water will depronate a proton here and push the electron back to the oxygen here. So, and then that electron can cancel this positive charge. So the final product will be this ester. This is actually ethyl acetate, a very common organic solvent, actually. Okay, now let's talk about the hydrolysis of ester. This is basically the opposite of esterification. So if we have already the ester, like I use the ethyl acetate again as example, react with water, and you also need acid as catalyst. And then this will produce carboxylic acid and alcohol. So this is the opposite of esterification. So let's look at the mechanism. You will see the mechanism is also pretty much the opposite of the last slide. Now, first, the ester acetate, ethyl acetate will be protonated by the acid here. So the lone pair on the oxygen attack this proton, protonation happened, and then this carbon here will be more electrophilic. Then water as the nucleophile will attack this carbon, the oxygen's lone pair attack this carbon and then break that pi bond and then form this tetrahedral intermediate. And now you can notice that the proton need to be deprotonated, so it will do the internal proton transfer. After that, you will form this intermediate again. Now the proton will be on this oxygen. So this oxygen will be positively charged, and also this will be a good leaving group because you can see this is an alcohol. The leaving group will be kicked off by the lone pair of oxygen pushing back to form the double bond and then kick off this leaving group as ethanol. And then you will form this protonated carboxylic acid. So last step, you need to deprotonate this proton on this oxygen because you want a neutral product. Now water can be the weak base to deprotonate this proton and push back electron to the oxygen. And then final product will be this carboxylic acid. And the other byproduct generated at this step as ethanol. So this is the hydrolysis of ester catalyzed by acid. Okay, now the reactions of ester here showed. I will give you two examples of first react with Grignard. The Grignard will react with ester converted to a tertiary alcohol by two sequence. Okay, the first reaction is react with the Grignard. Second is actually work up with the acid. The example I shown here is the ethyl magnesium bromide as a Grignard, and I still use the ethyl acetate as the ester as the example, and the product here will be a tertiary alcohol. Now let's work the mechanism here. So first, the Grignard here I use the skeletal, so this ethyl group can be treated as the ethyl anion. It's a nucleophile. It's a very good nucleophile. And then this nucleophile will attack this carbon. This carbon is electrophilic. Notice that we don't have acid here, first step, so we do not have protonation. So this ethyl anion attack this carbon and break the pi bond and form this tetrahedral intermediate. This is actually an oxide here. So this negative charge will be balanced by this positive charged magnesium bromide cation here. So that's called a counter ion. And then this intermediate will have the oxide push back and form the double bond again, and then kick off this leaving group. That's ethoxide. And then we will have this intermediate. Actually, this is ketone, methyl ethyl ketone. And then this ketone will react with the Grignard again because this is still active carbonyl. And then this ethyl anion will attack this ketone and break the pi bond again. So make this another tetrahedral intermediate and another oxide here. And then this will be protonated by the second step, work up with acid. So this oxide can be protonated by acid. And then last step will make this neutral tertiary alcohol product. So this is the aeropussion mechanism of this reaction. So now if you want to make a primary alcohol, you need to use another reagent to reduce the ester. Okay. So now if we want to make a primary alcohol from this ester, we will use the lithium aluminum hydride as the reducing agent, and also we need work up with acid. The structure of lithium aluminum hydride is shown here. Okay, this lithium is the cation and the aluminum hydride is the anion. It's complex, and the real nucleophile is actually the hydride here. So you can see in the aeropussion mechanism, the hydride actually will attack this carbonyl in this ester and then break the pi bond as usual. And then this is the intermediate formed. It's an oxide here. So, and this oxide negative charge also balanced by the magnesium bromide cation. And then this negative charge, the electrons will push back and kick off this ethoxide as a leaving group. So the intermediate actually is the aldehyde. This is called ethanol. Ethanol is also active under this condition. The lithium aluminum hydride can further react with this aldehyde. So the hydride will attack this carbonyl of the aldehyde again and break the pi bond, same reactivity, to form this tetrahedral intermediate, the oxide, again balanced by this cation. Okay, now the second step is the work up with acid. So when there's a proton and then this oxide will take the proton. This is a protonation, and then final product will be the primary alcohol here. So we have choice, right? So it's flexible. If you want the primary alcohol, we can use the hydride, lithium aluminum hydride, to reduce the ester. If we want the tertiary alcohol, then we can use a Grignard reagent. Okay. If you have any questions, please let me know, and good luck to your study.